just so we're on the record. And let's go ahead and move on from here. So, always nice to have some data, I guess. So, from the last pre-class warm-up, and this was as of yesterday, probably morning, just assessing where folks are at, where the course is moving. As folks notice, it's pretty much a bell-shaped curve, which is about what an instructor wants. So if the course is moving too fast, come visit office hours. If it's moving too slow, most of the assignments will have like a little extra like going further, or can I try this, or just email me and say, hey Mike, how could I like improve this assignment? And those kind of things are welcomed as well. So wherever you're at, overall this is seems like a good distribution, but and don't worry where you're at on this curve either. Things tend to either click or get more challenging, I guess, as the course goes on. Either way, there's always plenty more to do here. But probably more important is just, for me at least, seeing what resources you're utilizing. So it seems like a lot of folks are using CPP reference. That is what I'm usually linking to and referring to. The reason being that that's sort of the default truth for C++. Can be a little bit hard to read though, so kind of using C++.com or CPP reference are good. Was happy to see folks were also using my YouTube stuff. I'm beating the Cherno, although he's quite fun. His tutorials are very good as well. And then some folks also listed some other stuff like W3 schools I haven't taken a look at, but and then Stack Overflow is popping up. So all good resources to know about, all pretty reliable for C++. So just a little bit there on the warm-up. This is what last year's looked like too, just to show you. It's pretty much a bell curve. So it seems like we're on track. Although last time I taught this was a Summer 1 course, so Summer 1 has its own challenges. It moves fast. How many folks have taken a summer course? Oh, folks, yeah, it moves pretty fast, especially if it's like OOD or Fundies or some of these courses, which I haven't taught because they seem like they'd be crazy in the summer. Anyway, so here we're recording. Just a little bit of logistics. I've released a new assignment. We're going to be talking about splines. So originally I had something else, but I kind of am shifting things around based on some input. But we'll talk about splines, what they are. You can just think of it as a word for a curve. Something very useful in computer graphics. I'll get to the applications, but that should be pushed to your repository already. If for some reason you're missing it, just let me know and I'll get that to you either before we leave today or right after class if you message me. Let's see, other stuff on the calendar. Let's just go ahead and take a look here. So again, Spline is going to be released, and the same sort of cadence here. So about 8 days or so October 6th when you'll get that in. And then your A3s are going to be due tomorrow anywhere on Earth, which let's go ahead and see anywhere on Earth. Again, just a reminder, let's see, here's where it is. The last place on Earth where it's still Wednesday, it's 6 or almost 7 a.m. So again, that means Friday roughly at 7 a.m. for you folks. Questions and other logistics or things going on in the course, folks? Anything? Yes, yeah.
I think you made a post about this on Piazza, but I just want to confirm that we have extra tokens for the wellness day.
Oh yeah, correct, yeah. So for those folks who didn't see, there was a wellness day email. I don't know if they sent it out to you folks, but in theory you get 2 wellness days, which I think there's some online portal you log into and say, I need a day off. So I guess the easiest way I could think about handling that for this class is just, here's 2 extra tokens. You can still go through the wellness portal because I think I'll get an alert about that if folks do use that. And do use them. I don't think there's any disadvantage, right? At the end of the semester or middle when you're studying for exams, like take advantage. So the tokens seem like a reasonable way to just say, hey, extend and however you want to use them. Spend them as you do. Again, remember the tokens, they're not worth anything at the end of the semester. You can't trade them, you can't split them, you can't, do anything. So do take advantage. Yes, thank you for reminding me about that. Other questions about course stuff going on? or logistics in the class? No. If not, all right, well, let's talk about some more C++ then. That's what we're here for. And last time what we were talking about, so really just kind of capturing it in a picture, stack and heap memory. So we've talked a little bit about pointers in the preceding week, and just how to use those, these tools that allow us to store an address, and then just also thinking a little bit more about where's things actually stored in a process. And in C++, we often have to think about this, but this is true of any language. So again, if you're coming from a Java or a Python background, all of this is still true, it's just sort of hidden from you in a way. But in C++, we get to think about every time that we do new, we're allocating something on the heap, usually some bigger block or something that we want to live a really long time in memory, and then we explicitly delete it by calling delete, or delete with the brackets if we have an array of something. Okay, and then we have our stack memory, which is the memory that's, its scope is within the curly braces. That can be things like, again, our local variables declared within a curly brace, function arguments, these types of things. So we're very frequently putting stuff on the stack, and then it's just pushing and popping off that stack, automatically managing that memory for us. And towards the end of the lecture, what we looked at where we have to be careful is if we either allocate something on the heap, but we sort of lose that pointer or that handle into something that's on the heap, we go out of scope, and that's how we get a memory leak. Okay? And then we also looked at another sort of scenario where if we have a pointer, maybe something that's global in scope, that points to something in the stack that maybe gets pushed or popped off. That's where we did that sort of weird example with the random numbers we were generating, and our G underscore pointer ended up pointing to like some random value. Sometimes we got lucky, sometimes we didn't. Again, just remember, it just depended on what was in the stack. So that was last time. Any questions about these ideas? We'll revisit them. We try to revisit everything probably 2 or 3 times, just in different contexts, but this will hold here. All right, so with that in mind, where we're going to start going eventually is talking a little bit about data structures and practicing with our pointers a little bit, what we can actually do with them. So this is a pretty useful chart that captures most of the data structures that we're going to look at in this class. So just for my reference, how many folks have taken 3000, the data structures and algorithms class? Some folks, I'm not expecting everyone had, so maybe 40% for the record, something like that, maybe less than that. So we will have to look at some of these things like array, stack, queue, linked list, trees, graphs, and we'll look at the performance of them because they matter which data structures we choose. So this will be a pretty good picture that I'll probably bring up a few times just to sort of orient ourselves. But we'll at the least have to know the differences between these data structures. I'm not going to ask you to prove anything like you would in an algorithms class or discrete in that sense. But we will want to know, like, hey, why would we choose an array versus a linked list for certain scenarios? Okay. So that'll be part of this class. And part of doing that will mean building some data structures from scratch. Again, that's just something we have to do in our code, so we sort of understand something. And again, our choice of data structure matters because depending on our data structure that we use, that's going to depend on how we store information, how fast we can access it, meaning how fast can we search it, or modify that. So usually insert something new or delete something. Okay. So we'll want to look at those trade-offs in the context of C++. All right, so with that said, though, we have looked at some data structures already, just the ones that are built into C++. Okay, we've looked at static arrays in C++, or what I'll slowly encourage you to use, std or standard array from our standard library. Okay, so we have these here. So for example, here's 2 arrays. Here's my array with 5 characters. Here's the equivalent. These are the same things. This one's just using the library version. And both allocate enough contiguous space for 5 characters. And we could look using size of just to confirm that a character, or a char as it's sometimes pronounced, is 1 byte. Okay, so in our memory, whether we're wherever we're allocating this, maybe this is in the heap or that stack, this is what it looks like, right? We've got 5 contiguous bytes in each of these data structures here. All right, and code-wise, if you want to run a sample, which is included in today's samples, here is, again, creating our arrays. Okay, and you can confirm that they're both 5 bytes. And that's true of even this one. Even though this one gave us some extra power, if folks remember, right? We could do dot length and those kind of things. But that's not part of the size of the actual memory that we allocated. So we can actually run this, and that'll still be 5 bytes. All right, so that's our static arrays. Now some considerations when using this data structure. Properties. Again, sort of surveying folks. How many folks have heard Big O or remember it? And discrete, I think most folks have some memory of this. If you don't worry. That's not what I'm going to be testing you on. But the properties of a static array, again, the size is fixed. That's the big thing. We can't really expand it. I say it's 5 characters. It's going to be exactly 5. But what about the actual properties of storing and retrieving data? Well, the access time is constant. So we call that O of 1, and that just means we can index directly into some array and get back the result, right? So I could say my array at index 0 and just get that result, in constant time, or my array index 1, etc., etc. I can say exactly or explicitly which element I want, and it's a fixed time. I don't have to search for it or look through 0, 1, 2, and then to get to the third element, or whatever it is. Okay, so that's what we mean by constant time. Now, as we've learned, there is some cost, right? Because when I'm using brackets, what am I doing again in the context of our pointers and what we learned? What does brackets mean on an array? It's a contiguous space. I guess there are 2 things that are sort of happening. So 2 operations. That's what the cost is. What did we say? Yeah.
It's retrieving the value at position 5. It's reading it and then kind of outputting it.
Yeah, we're reading it and then outputting it, or putting it. So the reading part of it is sort of dereferencing that pointer. And then the 5, and sort of figuring out which one we want, is the offset into it. Yep, and that's what gives us, whichever element we're looking at. Okay, so that's the actual cost. That's all there is to it, and it doesn't matter again which element we access here. Okay. Now, if I'm searching for something, in this array here of 5 characters, and I want to say, hey, is it here? We would call that O of n time, where n is the number of elements that we have. It's just a generic way to say, how big is this thing? So if I wanted to say, hey, is the character, lowercase m in here, I would have to look through every single character in this array in the worst case. Okay, so we say that's O of n, or a linear operation. I have to look through one thing at a time, and potentially everything in the worst case. Okay, so that's what searching would be. This is assuming unsorted. Did folks learn binary search or these kind of things in the street? Most folks are nodding their head. They're like, yeah, good job, Mike. If I didn't put sorted or unsorted here, then that time might change. Again, we'll look at binary trees in this class. If you haven't, or if you have, actually implementing them. But maybe a more interesting question is on insertion or deletion on this data structure. And I just told you, you can't really expand this thing, which is true. This is always going to be 5 characters. But let's say I wanted to. And in fact, we sort of can, because this is really just a pointer to something. But what would the cost be if I wanted to say, well, I want my array to actually be 6 things or 10 things? How would we sort of expand or shrink, I guess, this array? What would the operations look like? How would you kind of programmatically do it? You'll get the first bit. I'm going to give everyone a few seconds to think about it. Yeah, think about what a copy would look like, I guess. All right. Yes, sir.
The idea would be to create a new array of the size that you want and then copy all the elements from the old array.
Yeah, that sounds like a reasonable argument. So for folks in here, we would say, hey, we want a new array. It's going to be 10 elements or however big we want it, and then copy each of the elements one by one, and then we would have some extra space. That's exactly what we do. What would the cost be of that operation if we have to copy everything here? Would that be constant time or linear? Linear, yeah. We have to walk through each element one at a time. Now I know my systems folks might be saying, well, Mike, there's little tricks like memcopy and these kind of things, but it would be a linear, right? We have to walk through everything in this list. Okay. And yes, there are tricks always to make things faster, but linear is what we must do. So the answer, our cost to expand or decrease, as was said by your colleagues here, would be linear time, right? We must copy each element one at a time. Okay, and just to show you what this code looks like, let's actually look at some code here. Let's see, array number 2. All right, here we are. So let's actually populate our array. Here's my array. I've populated it with Mike here. I've got this funny character at the end. That's the null terminator that would just kind of indicate the end of our character array here, which is a string. We've got to talk about strings a little bit. But, the copy here, here's my copy. It's size 10. I think we can get away with bigger here. There we are. And then, as your classmates have said, we can just copy, for all of our elements here from my copy into my array here. Now, it looks like I've got a tiny bit of a mistake here. What's the mistake here? I've only got 5 things to copy from here, I guess. Okay, so we have to be a little bit careful here. That's why I like standard array, because I could have done my array.size or something. So I got to be a little bit careful there. And then, maybe we want to add some more characters, right? Because our copy has some more space, or we can change things. And, you can do whatever operations you want. Then I've just got a little function here to print these out, just to show you that this is working. Let's actually compile this, just so we're ready to compile some more samples here. Again, I'm going to compile this like this, always remembering -G. And there we are here. So originally we were able to allocate Mike, and not too creative, Mike with exclamation marks. So we're pretty excited about this copy. All right, so everybody okay with that idea here? That's how we would sort of expand behind the scenes, I guess, or if we wanted more space here. Okay. Okay, now there's some other things that we could do with this, I guess. But let me think about how to ask this. Well, let me just move on, because I want to show you something else. I am actually going to make you build that into a data structure, which I'll get into in a moment. Let me ask folks a question, though. How many folks think this is very elegant, I guess, here? I mean, it's okay. Right? We can write this sort of for loop here. We write for loops in Java pretty frequently. You saw I made this little mistake here with the size. So I didn't like that, so it's a little bit accident prone. I'm going to teach you some ways to make C++ a really fun language. Meaning, let me just show you the other snippet. So for a moment, just memorize in your head this for loop. Yucky, we've got this here. Integers, these are even kind of gross too, we're going to learn, because these could be negative, so I could kind of mess this up as well. So there's a lot of room for a mistake. So I've got another example that I just want to sort of tease in your minds right now. I'm showing you the same code, but how to do this in a one-liner. And you might not agree yet, but we'll at least try it and then see how you feel. That I can just get rid of all my loops, and just there happens to be a handy function, and it's actually called an algorithm in C++, just called copy. Okay, so this is kind of nice. I'll just let you look and absorb it for 30 seconds here. This is how we like to write C++ code, though. Just call standard copy, and then we've got this thing called begin here. I'll talk about what the C means later. It just means we're not modifying. This is const. We're going to say, hey, from the beginning of our array to the end of our array, put all that stuff in my new copy here. Okay.
Does it tell the size of the array? Does it only work with like null terminated strings?
Yeah, so for this one, because my copy is in the scope, if it's a stack allocated array, this is going to be something I'll emphasize later. It knows, since it's within scope, how big this is, that this is 10, that this is 5. For our other data structure we'll use, like if you're using std array or the std vector or any of these other data structures, they have a dot size, so it knows how big it is. Yeah. And we're going to learn exactly how it's sort of walking through that data structure. It might be as soon as next week. Yeah. But this is the way in C++. It's kind of cool, right? We didn't have to think about what I was less than. We didn't have to do dot size. There's no integer. It's just saying exactly what it means. We're copying something. So it's kind of nice. It's a very functional style way to do C++, which we sort of like. So depending on your thoughts on functional programming or whatever, this is generally a good thing here. So something to get excited about for next week and the rest of this course. Okay. Alrighty, so that's just a little teaser of what's to come here. All right, so just a little bit more eloquent, these sort of one-liners we got. All right, but in any case, this was still a little bit messy to deal with, especially if we knew, like, hey, maybe we're going to have to resize that character array that held some string, my name, or whatever information we're holding. But luckily for us, as you folks know and have used, again, if you did the little exercise where we built our little text editor, or just from the homeworks have investigated, we have something called standard vector. Okay, and that is a dynamically resizing array. Okay, so std vector, a resizable array that's given to us. Okay, if we read this tiny text from the CPP reference page, it says, the storage of vectors handled automatically, being expanded and contracted as needed. Vectors usually occupy more space than static arrays because more memory is allocated to handle future growth. Okay, and we'll talk about that in a moment. But here's what it looks like. Let's go ahead. Let me go ahead and just open this up. Again, we can take a look here at our vector. So pretty much the same example. It's a vector of characters. That's what, again, the brackets mean. I just name it my vector, and then each of the individual characters. This is how we initialize, I should say, not our array, but our vector here, just to be specific, our dynamic vector, i.e. std vector, our dynamic array, sorry. That's, this is exactly what I mean. So that's how we set it up. We have different ways that we could set up a vector, but between the curly braces, this is what's called a list initializer. So we're just initializing it with 1, 2, 3, 4, 5 things. So again, it's 5 characters large. And then in order to expand our vector, we just do push back, okay? Which a better name for this would actually be append, which just means add to the end of our vector, exclamation, 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 etc. I don't really need this null character here, but there it is anyway. And that's the idea, okay? All right. So let's see. And then here's our example of just printing out our vector. I didn't do anything fancy here, but we're just iterating from 0 to our size. So my vector is some object. We'll learn about objects in C++, but it's got a dot size function we can call. And then we can look at my vector at some index I. Okay. Does anyone know what dot at does? I have the answer written above it, I guess, but versus using the brackets, right? The equivalent thing, I could have written my vector at I like this. It'd be the same in this context, but what does dot at get us that's more useful? Yeah.
It's going to throw an error if you're out of bounds.
Yep. Yeah, it'll give us a bounds check. So if I accidentally, I can't remember if I've done this yet, but if I put in 500 for the vector, it'll say, hey, wait a second, you only have 10 things. And that's useful for us. Versus if I just have the brackets, if I put in 500, it might throw an error, maybe. At best, we'll get a segmentation fault, and then we'll be warned. Okay. So anyways, there's vector. It's got some of these built-in functions to help us out here. Now, one question I have about this data structure, and you can kind of see how we're pushing back, one extra exclamation point at a time here. So again, we're expanding this data structure. And based off of our discussion earlier where we said, well, if we're going to expand something, we have to copy everything, move it over to a new array, and then it's going to be 6 characters. Then if we had a 7th, we're going to copy everything, and then add room for another one, so it's 7 characters. Does that seem inefficient to folks? Probably, right? I saw a head shake. So would it make sense that maybe every time we push back, our vector expands just a little bit extra? Maybe it's like, hey, I think you're going to do this again. I'll give you 2 spaces. And as your data structure grows, it kind of keeps saying, well, I'll give you 4 this time, and then maybe 8. And that's exactly what vector does. I kind of read as part of the description of vector that it does that. And that's sort of the question down here. That usually vector doubles whenever it resizes. Okay, so if my vector here is 5 characters, and then I push back 1 more, it's going to double and be 10 maybe, or maybe 12. I don't know, depending on what it decides. So this first pushback, is that a O of n operation, or is it a constant time? Which one? Let's see. The first expansion where it has to double, I guess. Let me be clear. And then I'll ask about the pushback. So I'm pushing back and says, hey, I don't have enough space. I've allocated exactly room for 5. So now I have to kind of do that copy, right? So what's that going to be?
That'll be O of n.
That'll be O of n, yeah, the first time. But then when I push back here, the one after, I've got a capacity of 10, right? So if I push back and it says, hey, I've got room, does that cost me O of n, or is that going to be constant time? That'll be constant, yeah. We have enough room, right? It's just like, if you have room in your house when you buy something, right? If you've got room, you just bring it in. You don't think about it. But if you got to cram in one last thing, maybe you have to spend some time sorting stuff out or whatever. So most of these operations are just going to be O of 1, which is nice. And then on occasion, maybe when we get to the end here, we're like, oh, that's the 10th spot. We better, double again or whatever. It'll double. Okay, so that's how vector works. And generally that is pretty fast. Okay, so we like vector in C++. Right, and that's just a heuristic, right? You could say, well, maybe we want to multiply by 1.5 or 3 or something, but 2, I think if you actually look, I think it might be 2 or 2.2. Like they empirically said that's a good number. So that's to avoid copying so frequently. All right, so here's sort of what vector looks like, right? And I just said, here's my vector. So even if I, ask for 5 things when I initialize it, I might get 10, get a little bit of extra space here. So those pushbacks are really fast. Okay, makes sense for folks? All right. All right, so vector, standard vector, the size isn't fixed, right? We can allocate on the heap and expand our vector, right? So we just say, hey, I need this time 10 bytes, a new char with 10, and then we kind of reassign some pointers to different memory. We'll actually do this so you'll really have an intuition, but that's what's going on. And that's how we avoid it being a fixed size. But that said, we still got handy, behind the scenes, this is still an array, right? So these are just blocks next to each other. So I still get that constant time lookup, right? If I just want to access something, I just say, hey, give me my vector dot at, position 3 or whatever. 0, 1, 2, 3. Okay, I know exactly how to do that. Okay. So we still get constant lookup time. Search is the same. Again, assuming it's unsorted. If I'm saying, hey, is there a S in this vector? I'll have to look through every single character. Okay, and then insertion and deletion. As long as we're inserting onto the back where we've got room, right, where this gray space is here, where it says, hey, this is our extra capacity, O of 1, right? Most of the time. It's just constant time, unless we have to expand. So we would call that sort of an amortized, or maybe a better way to write this is on average O of 1 cost, okay? If I do something weird, and there is a dot insert function, I shouldn't say it's weird, but if I say, hey, I want to insert, into the 3rd position, that's going to cost me though. So then I have to sort of say, okay, I've got to make a copy of this. I'm going to take the first 2 things and put them there, insert the other one, and then walk through each item at a time. Okay. So that's where you can be a little bit expensive. And these are things to think about with our data structures and so on. How many folks have ever done LeetCode or HackerRank or any of these things? Yeah, a few folks. And you might think about some of these questions where they ask you about, hey, I've got a collection of stuff and you need to insert. Are you inserting in the front, the back, in the middle, how often? And that's usually clues on which data structure can be efficient. I think there's I don't know what it's called, but here at Northeastern, there's an undergraduate club for coding competitions. Is that true, or does anyone know the name of it? I know it existed for a while. Okay, well, I know there's one at least for like high performance computing. That might be something fun to look at, I guess. Alrighty. Well, anyways, so with arrays and so static arrays and vector, which is a dynamically resizing array, we have a few programming tools that we can use now. So let's try to use them to solve some sort of problem, maybe something that's interesting. All right. And the problem that we're going to start solving is by doing something a little bit graphical with what's called a spline. Okay. So spline, you can just think of as a curve. It's maybe a weird word, but my sort of domain is in systems and graphics, so you folks will get some graphics things here. But basically, it's just some curve here. So I'll show you some examples. Here's what a spline looks like, and this is what you're going to be implementing for your next assignment. Some curve where basically you can just put a few points. So these points here, you'll notice, are sort of defining our curve, and then our algorithm, our spline algorithm, is going to draw a nice smooth curve that either passes through all these points or is approximated by these points. Because you can imagine it being kind of tedious or maybe expensive to store all these individual points in a vector or something. Why not just say, hey, there's a few points here, draw the curve. That seems kind of reasonable. So that's the idea. Let me give you some more intuition here. And again, there's many different types of curves. So they're one type of many different curve drawing algorithms or whatever. This one here, just so you know how it's pronounced, Bezier curves. That's a popular one using graphics. We're going to be implementing Catmull-Rom in this class, Hermite curves. And they all have different properties regarding how continuous they are and so on. So if you go into graphics, or if this is something interesting to you, we can talk about what makes one better than the other. There's different properties depending on what you need to do. Okay. But again, why are spleens or curves used? Well, again, they allow you to easily approximate the shape, again, just using a few pieces of data. Okay. And depending on if you, again, assuming you are trying to draw a smooth path, just using a few pieces of data, a clever algorithm, you get this nice sort of smooth movement versus something like this. Okay, that's very hard turns. Again, you could imagine this. I think I'll show an example in a minute. In the context of a computer game or maybe a simulation. Let's imagine you're in a world and you see a character walking around like this, and then they just do something like this. It's very robotic, right? If they're just sort of making these hard turns. So often, we use these sort of spleens here to sort of, have a nice natural motion of how someone might actually, be walking through the world. And you also get a little bit more information here too. If you have a curve, for folks who have taken calculus, right, you can kind of use the slopes to figure out, your acceleration as you're sort of turning a corner, and again, get a really nice natural movement. So it's kind of cool here. So here's some applications. I've got some different videos, but if you've ever wondered how in Google Earth or games or something they're trying to draw a road, they can kind of approximate it in this way using different curves. So there we go. If you watch this video, which will actually be one that's linked, I highly recommend you watch it. It'll show you how to implement what we're doing. The author here will tell you about, hey, how do I make this point follow nicely along this curve here. Okay. All right, some other applications. Again, maybe you don't care about games or these kind of things, but in graphics it's pretty neat. If you want to do 3D stuff, you can actually just draw a simple curve and then sort of extrude around that curve and then get some shape here, like this face. Here's a few other examples. Again, just drawing a curve and then generating some shape here. I don't know exactly what they're trying to represent here, but something. So if folks are more in the media or CAMD and doing 3D stuff, this is kind of neat. And here's where the name comes from, Catmull-Rom. I guess I gave away the answer here. Don't look. Does anyone know who Ed Catmull is? Well, he's one of the founding members of Pixar. He's the president right now. So that's where part of the name comes from, and then the other half comes from Raphael Rom, who strangely I think went on to work on like computer networks or something not related to graphics. But they worked on this together, which was kind of cool. So Ed's a pretty interesting person if you're interested in graphics for his contributions. All right, let's talk a little bit about implementation here to get you thinking about things. So here's an example. And again, you can kind of see just these little points here, P0, P1, P2, P3, etc. And the type of spline that we're doing actually will pass through all these points, which is kind of cool. All right. So, how do we draw a spline? Well, again, the idea is going to be that we're going to plot some points in some way here. And then, based off of where some of the neighboring points are, that's going to influence how this sort of curves. Okay, and again, you can notice that it's not. I guess there's some parameters that we can tune, but again, it's not just like a straight path here. It's actually kind of curving here like an S here. And maybe let me draw a few curves on the board here. Let's get a chalk here. Test our math knowledge here. Oh. Let's see, I've got an abundance of erasers, but no, that's okay. Here, let's do this. Then everybody gets it on the recording. Let's see here. Draw a curve just to, again, give you some intuition about what's going on here. Okay. All right, so here's our x-axis and our y-axis. Again, always label your axes. Okay, if I draw a line like this, folks would say this is, what? Would they say this is linear, quadratic, cubic, something else? Probably linear, yeah. I've done my best. What about something like this? Oops, let me draw it a little bit more gently. That's probably more quadratic, yeah, probably like x squared or something. What about something, how to draw this? I should have had to, I'll graph it. We'll take a break here in a second and I'll graph it. I'm trying to visualize it myself. Something like this that kind of changes directions. Well, I guess this is what we're going to get into. This one's probably going to be cubic here, but we need to also sort of change directions at some point. So what I'm trying to get to in this picture, if we look at from P1 to P2, it's kind of heading in this direction, but then it's got to kind of curve and make an S and then wind back. So this is going to end up being a cubic function here. So we'll look at how to do that in C++. All right. So here's a little bit on the intuition here for a Catmull ROM spline. And given 4 points, so and I'll provide an example today, and we'll talk about how to do some actual graphics. You'll plot 4 points, and the only place where you're actually drawing a curve is between the 2 points in the middle. Okay. Now these other points on the edges sort of influence this sort of curve or how it's drawn. Okay. I'll show you a little demo in a second for how these get influenced. Okay, so that's the idea. Let's see. And then as far as the curve that's actually drawn between P1 and P2, well, we could imagine just kind of cutting this curve into little tiny pieces. You can kind of think of it like, hey, I'm 50% through the curve, and that would be about here. And here's, this looks about like 80% or so through the curve. So that's what T is. It's just going to be some parameter that's between P1 and P2. And that's how we're going to sort of plot some points here. Okay, we call this interpolation. So we have one point here and another point, so we've got to draw something between it. Okay. Now I'll back up and revisit that point in a second here. But let me show you a demo. So you can click on this and kind of play with it later and kind of move around some of these points here wherever you want. But you can kind of see how one point just kind of influences the other. So even as I'm moving this one around, sorry, let me move this up a little bit. So as I'm moving this point around, you'll notice that it's still influencing this curve, even though there's one point in between it. Okay, so if you kind of just look at the red for a moment here. Now what you'll notice in the blue behind the red, so it's a little hard to see. Let's make it a little up. I guess this app doesn't really want to zoom, but you'll see just the straight line that's drawn in the blue here. Okay, and that's our sort of rigid, not smooth, not nice curves. Okay, so that's just a little demo you can play around with here. All right, but let me back up 1 second. I use this word, interpolation. Again, maybe you've seen it in math, maybe you've seen it at some point, maybe not. That's fine. But that's part of the magic of splines, is this ability to, we say, interpolate between two or more points here. So just looking at the simplest example, if I have 2 points, I've got a point here, P0 in the bottom left, and a point here, P1 at the top right. If I wanted to say, hey, I know the coordinates of P1 and P0, and just linearly, so just draw a line, so the most direct path. If I said, hey, I want a point that's halfway, I would say, okay, so halfway, that's T here, 0.5. Doing linear interpolation, I would say, well, that's right here. Okay? So you can imagine, again, plotting a bunch of points along the way. All right, this is something you sort of do when you're driving somewhere. You say, oh, about halfway is here, and then you sort of know where that location is. Right? So same idea with our points here. And the formula is not too crazy or anything. If you want a little bit of intuition, here's a video of some guy explaining it. But in this class, we like using our standard library, so we've actually got a LERP, or linear interpolation function, that gives us the location between 2 points. Okay. If you actually want to see how it's calculated, because it's kind of useful, here's how we calculate it. So they just say naive LERP here. It's simple enough, we can just use LERP though. Okay. So here's your input, your A, your B, and then how far along do you want to get from the value of A to B here? Okay. All right. So that's the idea. Let's look at a quick example here. Let me open up some code. So you have a little code example if you want here. LERP. Here's the naive LERP function, just in case you want it. Here's an example, though. Let's make it larger here. Okay, so you can see what's going on. And let's go ahead. Do G++ -G. Now this is a C++20 feature to have this function, if you can believe it. So you'll need to compile C++20. Otherwise, just use that naive LERP function. Right? You can just copy and paste this here if you want. It's the same thing. So LERP-O. And then let's actually run our program here. Sorry, let me rearrange this so you can actually kind of see. Here it is. Okay. Oops, I guess I didn't. Sorry. Move this over here. There we go. So all this is doing is it's calculating between the value of 0 to 1.0, and then it's stepping 0.1 along the way of the values between 0.0 and 100. Okay? So you can kind of see how we're just stepping. Well, if we're interpolating between 0 and 100, and I'm starting at position 0, how far along the way am I to be? Well, I'm at 0. That's another way to think about it if it's useful. And if t is equal to 1.0 at the very end, I guess it's less than or equal to, so it never quite gets there. Here, let's make it get to 100. Just making this less than 1.01 or something. There we go. Then we should get to the very end here. Okay. So that's the idea. Now 0 to 100 is not a super useful example. If we try like -50 to 100, that might help provide some more intuition as well. So again, you can kind of see where this function is useful, or eventually we'll get to the end. We start from the beginning at 0, and here's all the sort of intermediate values along the way. Makes sense how that works, or how we can use this function? Again, you kind of think about this when you're crossing campus and saying, okay, I'm about halfway there to class, to C++. That's the idea. Alrighty. Okay, and then this is part of the numeric library. So just to show you, or actually, this is part of the CMath library for the linear interpolation here. Okay, so you have to include CMath. Most of the time the compiler will remind you if you forget, but just in case. But there are other handy functions. So it says down here in lerp, defined in header CMath. Then there's other useful ones like midpoint, greatest common divisor, etc., etc. And we'll look at some of these where needed. All right. Okay, so one more slide, then we'll take a little break here. So the idea is, or again, just providing some intuition on curves, because they're kind of neat on what you're going to be doing, is if I have a point here, so here I have 3 control points. I'll draw your attention here. And if I was just going to draw straight lines, right, you can see this, look at this tent here. But if I have 1, 2, 3 points, and if I linearly interpolate from this point to the point that follows after, so I'm using some other control point. So remember with cat, mole, rom, I said there are 4 points, and we're going to kind of, the ones at the end will influence the 2 in the middle. Well, this is kind of the idea with a curve. So here I'm just saying, hey, if I'm 10% of the way, from this point to this one, but what if I'm connecting, that 10% to the 10% of the next one? Well, you'll actually see this line connect here, and then I sort of repeat that process and say, okay, I'm 20% between these two, so plot a point here, and then what's 20% between these two, and plot a point? Well, you'll see if I do that enough times, you get a curve approximation that shows up here. So that's kind of a neat result, or at least a neat way to visualize curves and how they work. Okay, so this was kind of neat when I saw this. I was like, why didn't my teacher just teach me that? So this slide is dedicated to folks learning curves, I guess. Anyway, so again, just for your intuition on these things. All right, so with that said, let's go ahead and take about a 6-minute break or so, or till 3:50, 7 minutes, and then I'll talk about how do we actually do this in terms of graphics, because we're plotting points now. So we need some library. All right, so we'll pick up there in about 7 minutes. Hi there. Yeah.
I double checked. So I managed to get this is for homework for me. So I managed to get the ASCII art.
Yep.
The only issue is that on like a PowerShell or like on the command line that I did this in, it gets cut off a little bit in here. However, that's okay.
Yeah, I think it's okay. I think it's just stretched. It just depends on like what font you're using, or so that should be fine. Yeah.
Okay. So all right.
I think it's fine as far as it looks like. I see my face for it.
Okay. Just wanted to double check.
Yeah.
All right.
that's
Thank
good.
you.
Yeah.
You always see the same thing.
Alrighty, folks. Let me get us back in action here after our break. And let me kind of rewind. See, did anybody have any questions on spleens or vectors or static arrays or any of these ideas? Just kind of looking backwards. Anything? No. All right. Yeah.
Quick question for this slide, actually. For this example, why did you include the null, the null terminator
Here?
explicitly?
Yeah, so in C++ and in C, I guess, we actually, strings are represented as a sequence of characters, so a character array. So if I pass this function into most of the C++ functions that take a character array or anything in C, basically those functions know to terminate or stop processing a string once they see the null character here. Now there are some kind of funny rules with like when do you explicitly use that or not use it. So just as an example, if you're doing a character array explicitly, we usually put it on because you're allocating space for the end. That counts as one character. Otherwise, it might just kind of continue on forever. And we kind of saw, maybe I can hack together something, or feel free to post on Piazza, like an example of where you call some string function that says, hey, I'm looking for that null character, and it keeps looking and keeps looking, and all of a sudden you're past your string, and then it just keeps looking somewhere else into memory. That sort of buffer overrun is another one of these security vulnerabilities. That's like one reason to put it in. Let's see. Actually, let me actually run this through in GDB here. Oops. Let's open up. So that was array 2, I think. Where we did this. Yep. Okay, so let's open this up in GDB. Let's make this a little bigger. Array 2. So we got to do some GDB every time. Let's actually just start this up here. Take a look at it. Okay, so if I go to the next thing, let's see. So I'll do Control X 0, or actually focus on the source window, so then I can kind of move up here, because this is what I care about, my array. And then what I want to do is, let's see, focus on the command window. So now I'm down here. Sorry, it's a little bit hard to see. But I can actually run this examine command. Did I do this earlier? Examine and the backslash? Maybe not. Okay, maybe not. I can examine how many things I want to look at. Let's look at 8 bytes, B for short, and characters. And then you can type in my array. And if I hit enter, then this is me sort of examining what's in memory here. Actually, let me get rid of this window because we don't really care about it. I want folks to be able to see the memory, so we don't need this here. So start. And again, for our LLDB folks, right, you're not really using the text user interface. Do next. Next again. Control L to refresh things. So examine /8 bytes. Interpret them as characters. So that's sort of the command my array. Hit enter. And then so starting from this address, which is where my array is, it's reading in the memory. MIKE. And then it has a null, and then it just happens to have some zeros after here, I guess, that it may be padded it with. But we can kind of see, we can kind of start looking into other memory and say, oh, maybe this is important. I don't think this is anything important here, but whatever this number is. So I could imagine some function that just says, you write it out as like print characters or something, and it just prints everything in your memory. So you'd want it to terminate at the null point. And then the sort of going off of that, so when do we need to include this? Well, if I just create a what's called a string literal here, if I just create Mike here, let's go ahead and recompile this, rerun it with GDB, start, next, clear, and let's examine 8 bytes of characters from string literal. This one actually happens to put the null terminator at the end for us. It's just something I guess you can kind of remember. You don't have to put it in like this. Yeah, I don't know. It's just something I kind of remember. Or actually, I think if I check the size of this, I think it might come back as 5. Let's see. Let's see if it counts it in C++. Size of string literal. So these are the kind of experiments. And again, I don't expect anybody to remember this stuff. I have to do these experiments to remember. But yeah, it does come back as 5 here. So in that case, it's like, oh, it must be putting the /0 there. Now we will learn about the string type. I mean, we saw stood string in assignment 3 at the least, and I've mentioned it a few times, and that does put the /0 for us. So we like that. That's a good abstraction. We don't have to remember some of these silly rules. Yeah. Let's see. Other questions about stuff? Vectors, arrays, any of those things? Copy. We'll look at some of these other ones, the algorithms, as we go.
Why do we need all the CBN and CN? Why can't you just put it like in there?
For these ones, for copy? Yeah, this one takes specifically what we're going to learn is something called a beginning iterator, a combination of a iterator for the start and the end of where we want our computation to perform. And this begin function specifically is a pointer to something, so our array, some location. Begin specifically says, hey, wherever the beginning of this is, and end will specifically find where the end is for us. I think there might be other functions, or we could imagine writing a function that just takes an index, 0 to whatever. It just depends what data we're working with. Because this is a little teaser. What if I had a data structure that was like a tree or a graph, for instance, that sort of like spanned out in different directions? Then an index doesn't really mean anything. We need to sort of know what the beginning is and then how to traverse it. So that's where the power is going to come soon. Or in a few weeks, I'll say. A few weeks. Alrighty. Other questions? Seth? All right. Awesome. Alrighty, so moving us along, we talked about our splines. Now, how do we draw them? This is the big question here. So how do we draw graphics? Well, we need a library to do that. So we're going to be using one called the Simple Fast Media Library. Has anybody used this by any chance? In another class or no? Awesome. All right. That's good. So we're on the same page here. So Simple Fast Media Library. As it's intended, it's supposed to be a sort of simple to use graphics library. That doesn't mean it's not powerful, though. There's been a lot of commercial games and projects that have used this. So, you could use this for your career if you wanted. But what it's going to handle is a lot of stuff for us, like keyboard input, mouse input. You could run this on your iPhone or Android if you wanted. There's ways to get it set up. We'll just be on our desktop. But we'll be able to just include this third-party library, so something that somebody else wrote, into our projects and get this functionality. Okay. Unfortunately, there is no include, graphics in C++ yet, or other things like networking. But that's all in this library here. All right. And then for our next assignment, since I'm asking you to actually draw something, spleens, we'll need this library. Okay. And it's specifically built with C++ in mind. And it's also quite well documented, which is going to be an important part, I think, of this class as we go on. One way to read or learn C++ is to read other code or see how folks sort of structure their programs. I think this is a nice library to do that with because it is well documented. All right, so we'll have a little bit of practice with that. So if you put SFML into Google, you'll probably get the web page, but here it is anyways, talking about it. There's a really nice Learn section, so you can go ahead and click on that, and you will at various points in the class. And within the Learn section, there is the tutorials and the API documentation. Okay, so it's relatively nicely laid out for us. Now there's a bunch of different classes or objects that we can use. Again, we haven't really talked about classes yet in this class or how to build them in C++. In fact, I'm going to try to push that as far as I can. So you'll notice classes and stuff being pushed back, but we do have some things that we're going to want to build. Things like, or use rather, in SFML, like different shapes and how to create a window and those kind of things. So we will need these in SFML. Here's just an example, again, if you click on that list. But the important thing, or what I'm highlighting here, is you're going to notice our functions or objects that come from the SFML library, they're going to be prefixed with SF:::. Okay, so that's the, again, in Java, you'd think of this as a package. In C++, we call this the namespace, where we have SFML libraries. Okay, so that's how you kind of know which documentation to look at. All right, and then just a few notes. The tutorial page is quite good for getting started on Windows, Linux, and Mac. And I have some videos as well, which hopefully we should get to at the end to start getting you set up. So let's just go ahead and start with creating a window in SFML. How do we do this? Well, the first place I would again look if you're wondering how to do something like this is on the documentation. So I'll try to link these kind of things. We'll get kind of used to the links here. Let's just go ahead and click on it. So again, if I went from Learn, API documentation, let's give this a moment to load up. There we go. Then I would click on maybe, well, maybe I'm lost here. So I go namespaces, modules. Okay, this seems like a window thing, so I'll click on window. And then there's all the different kind of window things. Click on window. And then I can see all the different things that I can do to create a window. So here's the constructor, or how I would build one, and then some member functions or methods that we could call on it, getting the window position, setting the position, etc. Okay. All right, so that'll be the idea. I'll show you some code in a few moments, and we are going to learn about some things like inheritance and those kind of things. So if you've taken OOD, you're familiar with inheritance and composition. We'll learn those again in C++, but you can see the little diagrams here, which are quite useful. All right, so that's on a window. How do we create one? Well, just starting off, what we've got to do in SFML is include some new functionality to do graphics things. So again, that's sort of our keyword. You'll notice at lines 9 and 10, I'm including in the less than and greater than sign, the wickets, sfml/window.hpp, sfml/graphics.hpp, and that's going to give me new functionality for doing things like creating a window and drawing some graphics on that window. Okay, so this would be sort of a basic or primitive SFML application to see if things are working. You'll see in the comments here, there's a bunch of notes on how to actually compile this thing, which I'll show you what to do in a moment. We've got to talk a little bit about this. Because the idea is we're going to, in a moment, have to download SFML, so from the website. And depending on if you're on Windows, Linux, or Mac, you'll have a little bit of a different setup for how to get started. Okay? And in secret, that's half the battle of this assignment. The spline part's actually not meant to be difficult. It's to get your environment set up for the rest of the semester. Which for some folks is just going to be a snap, and other folks, I don't know, Windows will push a weird update, and then we have to figure something, or whatever operating system. Last year it was Macs came out with M1s. For how many folks have an M1? You should be good to go now, but last year that was weird for some reason. But that's the idea. All right, but let me show you some actual SFML code and kind of orient you a little bit here. So inside of our sample code, again, where you can find all this stuff here, module number 7, there is an SFML folder. So let's go into that. And I think I just start off with, well, and this next slide is simple2.cpp. So let's open that up here and let's have a look here. All right, so for this one, let's see, and I think folks have been telling me it's a little bit easier with the lights off, so sorry, I forgot earlier. So same rules apply. We've got our entry point here. Again, we'll notice that we have our, including the header file for our new SFML stuff. Graphics, I think, includes window, but you could include window or whatever it was here, window.hpp. There it is.
So can we link against like window graphics and system even if we don't necessarily include them?
You can still link against them if you don't include them. Yeah, are you looking at this Linux line here?
Can I just write an alias for that?
You could, yes, as long as this will work on your machine. In the Linux one, I'll talk about paths in a moment. You'll notice in the Mac one, we are explicitly saying, hey, where do these header files exist? Most Linux folks, if you just install it by typing something like sudo apt-get install, it'll add that include path into your system. So your compiler always just looks in a specific place and says, hey, is there any file here called graphics.hpp? So you don't have to worry about it, which is kind of nice. Yeah, that's coming up in a moment. So read my mind. Let's see. So anyway, just getting set up. And some of this will come from the tutorial, but right here's how we create a window. Right, we've got a window object again in our SF namespace. And then the parameters you can kind of look up, but we're going to create a window that's 400 by 400. This example is called the circle on mouse. You'll see that in a second, where I draw a circle wherever my mouse is. And then we have functions like below here, or rather types here, circle shape. I name it shape, and it's going to have a radius of 20. And then I set some properties of it, like the color here. Okay, so in this namespace, we've got something called an enumeration color for green. And that's going to set it up to be, whatever the pixel color is for red, green, blue value, right? So that we either RGB. So 0 for the red, 255 for the green, 0 for the blue. All right, and then graphics applications, they're supposed to run forever typically, right? If you're building a game, or until somebody explicitly says, hey, I quit. So usually you'll have some sort of infinite loop that looks like this. While the window is open, so until you close it or click the X in the corner, you'll have this structure then where you're listening for events that take place. So what's an event? Like if you move your mouse, that's like a mouse move event. If you click the left button, that could be a left click event. That's how applications handle different events that happen. So within this infinite loop here, you'll have another infinite loop that says, hey, if something happened, so we're polling, someone's sort of asking or listing for or collecting what events happened, we'll handle any of these events that might have happened here. So an event type where I closed, okay, and this one would specifically be, did the user click the little X in the top right or top left-hand side of your window? And if they did, close the window, and well, because the window is closed, this condition is not true, window is not open anymore, and then your program terminates this loop. Okay, so this will be the structure, these few lines that you see in every graphics application at SFML, or most every one. Right, it's a good starting point. All right, and then what else is happening here? Well, here's the more interesting parts, I guess. I'm using SFML to, starting from the right side, I'm getting the mouse position here. Okay, so I'm just saying, and these are sort of, I've got to talk about sort of syntactically what this means here, but there's some globally or statically available thing, our mouse, that I can just get the position, right? We usually only have one mouse. And we're going to say, hey, when it's over what specific window, what are its coordinates? Okay, so it's local position. And we store those coordinates in something called a vector 2i. What do folks think this is? This is an overloaded term, vector. Right? We learned about dynamic vectors today, which were the resizing arrays, but what do folks think 2i is here? Yeah.
Is it contents are tuples of two integers?
Yep, it's just a tuple with an x and a y position. Yep, so two integers. The suffix here usually is an indicator in most things what it is. There's also 2f if we wanted floats, but here we're being really specific. Mouse coordinates are in integers. So there we have it. So that's stored in local position, and then we can see how we're using this for our shape, which is up there, the circle. We're saying dot set position to local position dot x. Again, that's from our tuple, and then dot y. Okay. And then what do? Well, 3 steps again that you'll see in pretty much every other graphics application. We clear our window right away, so we give ourselves a clean slate. We say, okay, clean the window up. Again, you think about this like an artist or somebody erasing everything, and then we say, okay, on our window, draw our one shape, and then display whatever the contents are of the things that we drew. All right. So this is the sort of basics of a graphics application. Now let's go ahead and run it and see what happens. I'm going to take this line here, and we got to talk about this line in a moment here. Let's compile it. Let's at least see the program. Okay, so it compiled. And here's the application called circle on mouse. So, the circle is staying where the mouse coordinates are, or it's being drawn there. Okay, so kind of fun. Question, yeah?
What's the command compile on the same?
On Mac?
Yeah, on Intel.
Yeah, it'll be the same. It should be the same as the M1s as well. Sorry, I should just say Mac here, but should be the same. Okay, so that's kind of cool that we get that. Let's talk a little bit about this line here, though. I've got a few slides on it, and we're probably going to talk a little bit more in depth Monday about compilation. But what's going on here? Well, let's just take the first bit here. This should look relatively familiar, right? Our compiler, -G for debug symbols. This example is called simple2. We've been using -std equals whatever C++ version, and then we output the name of the program. All right, but what about these things at the end here? What do folks think here? What's going on? Yeah, good. Linking, yeah. I'm sorry, I haven't given anybody these terms, so if you've seen or heard of linking, or then you sort of know. But anytime I use the -L flag, this is going to search my operating system to say, hey, is there any library called sfml-graphics? Or anything, the convention on Linux is it'll be called lib-sfml, as one word, -graphics. And then this is just the shorthand. So that's saying, hey, I need this to link in or bring this library. So somebody else has compiled this code, and they've given me this file called sfml-graphics. Okay, and I've got to glue that code into mine so it knows what a circle shape is, or a render window, etc. Question?
Why don't we have to link when we're using like cout or like some of the like maybe do other includes? We've done that before.
Yeah, that's a good question. So why don't we have to link the other stuff? The truth is, let's see here. I'll explain some of these tools here. Whoa, let's see. Well, there's this little program here on Linux you can run that tells you all the stuff that's being linked for you. So as you can tell, this is a big list. So C++ is cheating whenever we compile. I'll try to find one. Here we are. Automatically, it's always linking in something called lib-std C++, which is where all of our C++ standard libraries live. So we haven't had to do that for cout or those kind of things. I'll try to remember and maybe do that explicitly. I think Monday I want to talk more about this process, and we'll do it manually. Maybe that's the right way to do it. Yeah. All right. Now there is one thing, and one of your classmates mentioned this. What about these files that we're including? How do we know how to get to these files here? Include, and then the wicket marks here, sfml-graphics.hpp. Well, this we usually have to explicitly also specify some path. Okay, so on Linux. Let's see. I think the path is something like user/lib. Yes, everything. And then let's see. Oops, sorry. I think include. Oh, I gotta find it. User. Include. There it is. By default on Linux, it's always searching this path here. Let's see if we can actually find it. S here. I don't know exactly. Oh, there it is. SFML. Okay, so it's actually always including by default this path for us. But how would I do this manually if I wanted when I was compiling? And let me at least do it once so it's on the video for folks. So I'd have to do, let's see, do I still have it here? Nope. I'm going to copy this. Oops. Sorry, let me just rearrange this. There we go. Copy this. put it at the top so everybody can see. And then I'd have to do dash capital I and say, hey, look in that user slash include, or let's see, whatever it is, slash, it doesn't autocomplete sometimes, slash user, include SFML directory, and dash I is telling me, hey, look for the header files there. I'm sorry.
You need to include the SFML subject you have as a prefix.
Oh yeah. So I will have to be careful. Yeah, let's see. So I should just be able to do include here. And I don't have simple. Let's see, what directory am I in? Simple SFML. There we are. And just like that. Simple 2. Yep. So that'll work here. All right. So on Linux, though, again, this include path is already, it's the compiler, G++, Clang++, whatever you're using. It's smart enough to say, hey, they're probably, including some stuff in there. We'll just search that path by default. It's in a environment variable called path, specifically where it'll look for that. All right, so questions on that process? Or I guess there's one other thing to mention about this. So along with this include path, there is also a library path that we would need to say, hey, where do these files come from? Where is SFML graphics? So we do dash capital L. I think that's in user. So you got to search again. User, lib. It might be like lib. So again, everything's prefix lib, SFML. It'd be something like slash SFML dash graphics.so, something like that. But the actual directory would just be dash capital L slash user slash lib. Okay. Does that make sense for folks? So I have to say, hey, where do I find these actual compiled libraries so we can glue them in, and where do I find those header files? Okay. And just to show you that those header files exist, again, if we look in user, include SFML, here they are. And if you want, you could actually look at the source code. Let's look at circle shape. And here it is. And again, it's in the SF namespace. Here's like the class, shape, and some other stuff, the actual library. Right, here's some of these functions and so on. Okay, so that's kind of cool. We can actually look at how this stuff is implemented too. So questions on that and the compilation? You're going to see a couple of videos that I provide that show you how to get set up on Windows, Linux, or Mac. And the tutorials are pretty good. So you'll have, whichever way you want to start, with a video or a text tutorial to get started. All right, and here's one more example that I've included. Let me open it up here. Let's do it here. Vim. This one's called lines. So let's just go ahead and do this. Lines. Oops. Okay. So, I'm glad I made this mistake. So what's this example doing? Let me show you what the example is doing first. Get a little bit bigger. This example is just going to show you how to plot some points, which is what you're going to be doing for your homework. You can use this as an example. For your spline, I'm going to ask you to plot at least 10 points and draw the spline between it. In fact, I'm going to give you most of the spline function. Again, the homeworks should be relatively quick, I think. But so here's a bunch of points here. So some pairs or a tuple that we have here. And then there's a function to linearly interpolate between the points and then to draw them. Okay, that actual vector. Okay, now why did I get a crash here? Let's see if someone can spot it when I run this. Lines. Let's see if there's an error here. So here's my compilation. This was subtle. It's a very subtle thing, but you might run into it. Yeah. Yeah, so I think by default, G++, depending on what version you have, will be 14. But I said, hey, if you want to use that linear interpolation thing, it's a C++ 20 thing. So there we go. And then now I can run this program, and this program just interpolates between a few points, so you can see how that lerp function works. Okay, but you'll be writing your own linear interpolate or spleen or whatever you want to call the function to actually draw something. Okay, and that's really the primary objective of A4, to get you thinking a little bit in graphics, as well as set up for SFML, because we're going to be using that the rest of the semester. Questions on this stuff here? Okay. Let me flip through a couple slides. I think we've covered everything. So again, I'm going to talk a little bit more about compiling and linking, but on the slides, again, the SFML tutorials are good. I've got a few videos on every platform I can think of. Or not every platform, 3 platforms, Windows, Linux, and Mac, to try to compile this and explain linking and these kind of things. And we're going to talk a little bit more in depth about what header files are, libraries, these kind of things, so we understand the C++ compilation process. I think that's super important, and it never gets taught, unfortunately, unless you take systems with me. Or the other instructors, they teach it too. All right, so anyways, include, that's just essentially copying and pasting and saying, hey, you have these functions available, but then we need this other step, linking, which says, here's the actual implementation, here's how we actually get the work done. Okay, and that's what the SFML implementers maybe secretly did, and they compiled the code for you, and then you just glue it into your executable. All right, so we'll revisit this soon. Now, I do recommend, I'm working on a Linux machine. That's what you're going to see all the examples. So if you can set up a virtual box, if you want to install Ubuntu, there's a few slides on this. It'll also be in your homework, so that's part of the homework. I'd recommend that if you're on Windows, for instance. It just makes life a little bit easier. You don't have to. Mac M1 users, you have to just use M1, and that's fine, and you shouldn't have any problems. My video will show you installing on Brew. So if you've used Brew before, you just type Brew install SFML, and you should, for the most part, be set up. Okay. Windows users, you can try to use the Windows subsystem for Linux too if you want, but otherwise, VirtualBox is a great option, and you just install Ubuntu. All right. So just a few notes on that. If you don't like VirtualBox, Northeastern has various free software for VMware. So that's a link on that. And again, if you're still struggling, take a look at my videos or these videos. We'll get you set up. That's the main goal. Let's see, extra stuff. If you want to build a makefile and these kind of things, if you know what those are, you can. We will talk about them eventually, but here's one that works. And then my exercise, if we have time, we have a few minutes, is if you want to try to get started here. Let me pause. Any questions? All right. Let me give you a 1 minute. If you're on Linux, you should be able to just type in sudo apt-get install SFML. I think that'll do the trick. Or either SFML-dev. What is it? libsfml, something like that. SFML. Yep. Here, let me show you how to install. Go to the tutorials, go to Linux, and then type in, libsfml-dev. So Linux folks can try that. Mac folks, what you can do, brew, package manager. Mac folks, if you don't have Brew, I'd recommend installing it. You copy and paste this, run it in your terminal, and then you'll similarly just be able to do brew install SFML. That should work for the Mac folks. For the Windows folks, let's see. I can't remember exactly what to do. I think you download the actual files, and then I've got a video on it. Let's see. So you should be able to just follow along. Where is it? With Visual Studio, I guess they've got the instructions. All right. I've got one how to do it on the terminal as well in my link links. Yep.
When it asks us for a path in the terminal, if we use the virtual box that you has installed, the pass just user, right? Is it the same password
Yes,
that we
yeah.
have to like, log in?
I think my VirtualBox already has SFML on it as well, so you don't really need to do anything then. That's the other bonus, yeah. So if it's running and it's running fast enough or whatever, you're good to go. All right, other questions for folks? All right. If not, I won't see you before the weekend, so have a good weekend. Post on Piazza if you have trouble getting set up. That's probably the hardest part with the next homework.
Have your weekend.
All right, thank you.